Give me a second to start recording.
Sure.
You have to highlight my phone? Yes, it is. Get your size good. We're in roll.
Okay, thanks everybody for showing up. We have Dr. Sam Gross here from Noblest, and he's here to talk to you about math and cryptography. So here he is.
Thank you. Thank you. I'm an emergency fill-in. My name is TBA. And I am officially licensed with the yellow badge now to speak out loud in public. So I'm official. It's all official. So about an hour ago, I took half a dozen talks that I've given over the last year to various clients, etc. Merged them all together and stripped out any of the sensitive or classified parts. And hopefully it works and there's something interesting left. Okay, so some of my favorite things. Did I promise you on the first slide some memes? I don't remember. It was promised. Okay, here we go. So at Noblest, we followed with bounding laughter what happened in the FBI versus Apple case, and these are some of our favorites. My particular favorite is up in the top right corner. So in the interest of time and making this appear to be an official talk, I'll pause for a moment while you read those so I fill up the whole hour. All right, that was a moment enough. So some other of our favorite current events. You might have remembered at some point in time getting a notification from LinkedIn to reset your password, right? So a big problem happened there, and I have one particular case that really illustrates what happened quite well. Everybody knows our friend Mark Zuckerberg. So he was affected by this, and so he's admitting something in this picture, I like to think, and was that his password for at least one of those sites was the phrase da da da, and that site hashed his password with MD5, which you'll learn in the next talk. My colleague Mark Sanders, that's a horribly bad thing to do. Does anybody know the reference? Poll the room. Anybody know the reference? Not at all. So I know this. It's the 1980s hit song by Trio with the same title, Da Da Da, made popular in a 1992 Volkswagen commercial. I hope they got that. All right. So there's my plug for Mark's talk. So the RSA algorithm, anybody know what the initials stand for? Yeah, those people. It's their initials of their first last name. I love that picture on the left, one of my favorites. 1977, and we're still using it. 1977. Fun math fact, because that's what I do. All the mathematics for RSA was laid out by 1670 by Leonard Euler. All of it. There has been nothing, no new developments in RSA since that, mathematical development since 1670. So how it works. So I talked about this last year, so I guess this is kind of nice. I get to follow up on it. So I won't go I won't bore you with lots of mathematical details like I did last year. So we picked two really large primes, right? So right now they're like 300 digits long, 300 digits long prime numbers. We multiply them together and we get a product. The product is what we call public key, and that's the information that's used to encrypt a message. So I send you my public key with public instructions saying, here, use this big number I just gave you to encrypt whatever message you want back to me, right? And the reason why I can decrypt it and read your message and no one else in the universe can is because I have some secret information, and that's the primes that I started with, right? So what's the mathematical process that breaks RSA? It's in that picture that Emma's brother drew in crayons a little while ago. Yeah? Yeah, so factoring. The factoring problem is what breaks RSA. So taking a number and factoring it into its constituent primes. So on the right here, that's exactly what's happening. So there's some other information in the picture. Does anybody notice anything else in the picture? So the primes are given 2, 2, and 3, and 2, 3, and 3. But they weren't just listed, some of them were circled as well. What's the significance of the primes that are circled? It's math talk, you're supposed to participate. No? So that's the primes that they have in common, right? We call it the greatest common divisor then, right? Okay. Well, it turns out that if you have two numbers, it's really easy to calculate the greatest common divisor. So the question is what if we have two public keys that share a prime factor, one of them, right? So user 1 picked the primes P and Q, and user 2 picked the prime P and some other prime R, right? And remember, those are given out in public to the whole world, right? And if an adversary or somebody in the middle calculates the greatest common divisor, they'll recover P. And simple division will give R, and you have Q and R, and give the keys to the kingdom, right? And calculating the greatest common divisor is pretty quick. For numbers of this scale using 300-digit primes, it took 0.0314 seconds on my laptop right here to calculate the greatest common divisor at that scale. That was a Pi Day pun, but I know that was long past. But true, it was there, right? 0.0314 seconds. It did actually happen. So it's really fast. So what you would really like to do is scan the entire public-facing internet, right? And you're going to get something on the order of like 100 million public keys, right? Just from TLS certificates alone, right? And then what you would really like to do is see which ones you can break, right? So every pair of distinct TLS certificates, you want to calculate a greatest common divisor of, right? So that's on the order of like 100 million choose 2 calculations for those of you that took like probability and stats, right? Basic stats class. So that ranks up there with like intractable, right? Because you're looking at hundreds of years to do that. Okay. So this happened with a data set. This happened a month ago with a data set from November. And this is data from a scan in November 2016 of the entire public-facing internet, right? All of it. And this comparison, pairwise, of every possible public key that's out there in the public-facing internet. And there's the results of how many of them share a distinct prime factor, right? Some people are still using export-grade cryptography at the 512-bit level. There's anybody still have like an old router from the 90s that's still plugged in to their internet at home? Yeah, I wouldn't use that. That's probably those 142,000 keys. And that's just from TLS certificates, right? That's not from all the other variants of the RSA protocol that are out there as a standard, right? Just TLS certificates. 1024-bit is the real scary one because that's still a standard. People still widely use it. Look at that, almost 13 million devices, servers connected with TLS certificates. So it's a surprising number. How long do you think this took for us to do it? Probably not hundreds of years, right? 4 hours. 4 hours. So our team at Noblis, we developed a really nice algorithm that does this massive greatest common divisor computation by not doing it pairwise, doing it in a very nice way, very clever way, I should add. So some wonderful developers that worked on that. Daniel, you helped us work on it. Raise your hand, Daniel. Yay. All right. Yeah, so the mathematics of it was absolutely fun, and I'm sure Daniel will say the software development was too. Yeah, so 4 hours. Oh, and I should mention, it's like an off-the-shelf box. A rather robust box that did it in 4 hours. So I think it has like 600 gigabytes of RAM, and the total machine costs like maybe $2,000 to do it. Yeah. So not that bad. And I think on a laptop, we actually did a test case on a laptop. We ran out of RAM for the 2048-bit case, but we did the 1024s in like 7 days on a laptop. Yeah. So it works. It works, and you can detect keys that are vulnerable like this. All right. So we hope that this factoring problem is intractable, and we just saw that it's very important to pick primes that nobody else in the world has picked when you form your public key. So what does intractable mean? Well, the next sort of standard in breaking RSA, so in 2010, a 768-bit key was factored. And that's the record factorization of a large number right now, 768 bits from 2010, at least the public record. So 1024-bit is like the next big standard, right? You might say that 768-bit really isn't standard, but when you start using it in like digital signature schemes and things like that, you'll see lots of variance in key sizes, right? So what's the cost of breaking it? So the record goes to Arjun Lenstra. Uh-oh, I don't think Arjun's going to pop up for us. Oh, yeah, there he is. The record holder is Arjun Lenstra, who wrote a paper in 2005 designing this really nice machine, a theoretical machine, and the development cost of building such machine was estimated about $80 million and specialized hardware to do this, and it uses an optical sensor, right? So when the computation that I'm going to talk about later finds a number of interest, rather than testing it to make sure it's what we want, an LED flashes on the motherboard. And an optical sensor records the frequency that the LED flashes at for that split moment in time, and uses that to probabilistically determine some interval that that special value lives in to follow up on later. So it can immediately determine lots of these values, right, at the speed of light, essentially, or very close to it, rather than plugging in a number, right, checking the output, see if it's good. Okay, now verifying the output, seeing it's good. Yeah. So with this special machine, that, by the way, has never been built before. It exists only in a paper. Can you wait to the end, Emma? Oh, okay. She's not going to wait to the end. I got time. It's all right. It's fast, like a cheetah. Okay. So it's never been built before. It's never been built before. It's in a paper, and the electricity cost in 2005 put it at like $70 million just to run that machine for a year to break 1024-bit RSA. All right. So I want to drop the microphone, but I need it here. We have a new heuristic as of like maybe a month ago. It's going to cost $0 in specialized hardware. And we can do it in a year, like up to a year. And to do it in a year, it'll cost like $65.7 million. So still a lot of money. I'm still waiting on somebody to give me $65.7 million to try. If anybody knows anybody, I'd like to know somebody too. We can be friends. But not on Facebook, because we saw what Mark did with that. Just let's not do that. All right, so I want to talk about how the state-of-the-art process works, right? So what was it Arjun Lenstra doing, and what research have we been doing in things like that? So just like in the case of where RSA came from, what did I say, 1670? So where does the mathematical ideas for breaking RSA come from? Not 1970, right? So everything that we have today for breaking RSA comes from a long time ago, an office far, far away. There was this idea of this guy Pierre Fermat, right? Right about 1650, before the math for RSA was even laid out, and he wanted to know, how do you factor numbers quickly, right? You don't want to just check divisors, right? That was really boring in elementary school, and it's still lame. So he rephrased the question to, how do we find squares, square numbers? Everybody knows what a square number is, right? 4, 9, not 17, 16 will work, right? Okay. Oh yeah, I even got a picture of it. Glad that worked. So here was his idea. What if we could find two squares, whole number squares, and look at their difference, right? We know from like 5th grade how a difference of squares factors, right? Just like that. And Fermat's idea was, well, what if we could find two squares whose difference is divisible by n, right? Then all of the factors of n would have to be spread out between the divisors of x minus y and x plus y, right? There's this bad case where, well, what if x minus y is 0 and x and y are actually the same, and all the divisors live in there? Then we get no information, right? No information at all. But if we can find two squares such that neither of these are entirely divisible by n, then we can take a GCD of, say, the number n and x minus y, and that'll give us back a prime factor, right? So that was Fermat's idea. So here's an example. I counted on my fingers for this. And you can, anybody have a calculator? You can check me, hopefully. N is 2041. You can pick x is 311 and y is 1416. And there's the squares, and there's x squared minus y squared. And there's the greatest common divisor of x minus y and n, and you get back 13. So what happens if you divide x squared minus y squared by 13? You can reduce it again and keep getting more prime factors until you don't have until you have one of these that are evenly divisible by the quotient. Okay. Any questions about that? That's like the highlight of everything. It's all downhill from here. Maybe. So where have we gone since then? So every modern factoring algorithm that's come around has relied on finding these differences of squares that Fermat looked at, right? Every one of them. So Dixon, 1981, had the first real big breakthrough in his random squares method, and that was a way of not going start to finish checking every square, but just randomly, some random number generator and looking at random values of squares and checking them, and that sped it up quite a bit. Carl Pomerantz, Peter Montgomery, and George Pollard are on there as well. So I have some pictures. There's Dixon. There's Carl. That actually happens to be Carl at the University of South Carolina from last year when we were having a conversation about something that I'm very proud to talk about today. So there's Carl, quadratic sieve discoverer. Peter Montgomery had an idea when he was coding this algorithm of Carl's of how to speed it up. So we'll talk about that on the next slide too. And then George Pollard had a very clever idea. There's George, for how to factor very special numbers of 2 to the k minus 1. Has anybody seen numbers like that before? Powers of 2 minus 1? What's that? Oh yeah, they could pop up there. But in terms of like factoring and primes, there's this great site called the Great Internet Mersenne Prime Search. And so numbers like that happen to be prime are called Mersenne primes. And those are actually very important for elliptic curve cryptography, for finding Mersenne primes. They make very good elliptic curves. But that's another talk altogether. So complexity analysis. Here's the runtime of it. So the Fermat method of just checking every square, right, is exponential time, runs in exponential time. And if you've had any complexity theory classes or anything, or looked at runtime analysis of algorithms, you'll see that these are now all sub-exponential algorithms, so they're faster. So Dixon's random squares method was looking at the outputs of the polynomial f of x equals x squared, right? And using those, right? And of course, bouncing around at random between values of that polynomial. Pomerantz's big idea for the quadratic sieve was to use x squared minus n to try to find squares whose difference is divisible by n, right? And you can see what happened in the constant. It went from the square root of 8 down to 1 in the exponent, and that was rather significant and set some records, which you can Google in the early 90s. So when Peter Montgomery coded this up, he found that the runtime increases exponentially as values of x squared get far away from square root of n. So the further away your input x is from square root of n, the longer it's going to take to check those, right? To check those. So he said, well, what if as you start to get far away from square root of n, right, you bring it back, right? You just do a linear composition or a linear shift. Everybody's done this in like in pre-calculus, right? Linear shift of the graph. Bring it back. Use two numbers a and b that are relatively prime, no divisors in common, to bring the input back close to square root of n. Right? Enormous speed up and set a lot more records. Cut the exponent in half this time, from 1 down to a half. Right? So Pollard's algorithm, we won't talk about it too much, except for it was for that special case. But Carl Pomerantz and some friends of his came along in 1992 and generalized it to what we call now the general number field sieve. And this is the state-of-the-art algorithm for factoring, the general number field sieve. And just to go back and forth, so look at the complexity, right? The power on the log n factor and the exponent for all of them is 1/2, right? The power is all 1/2. And the only thing that's changed is that linear constant out front, right? So the term in the runtime that's controlling, right, how long the algorithm is going to take, right? The biggest contributor to it is that power on the logarithm term, right? And what happened? It got cut from 1/2 down to 1/3. Right? Very, very big saving, and that was what is responsible for the 2010 factoring record of the 768-bit number. It took about 3 years of computing across academic clusters all over the world to do in 3 years, and was quite a deal. You paying attention? I put your picture up there for a reason. That's not you? Okay. All right. So how does it work? How does it work? So it should go back to this idea of Fermat, right? And if anybody's a little bit of linear algebra, you remember solving systems of linear equations like in high school? Okay, that's all you need here. Okay. So a definition. What we want to look for is we want to look for numbers that are smooth. So we pick some really big bound, and we want to find numbers all of whose prime factors are less than that bound. So if my bound is 10, right, I'm looking for numbers whose prime factorization is comprised only of 2s, 3s, and 5s and 7s, right? Doesn't matter how big the numbers are, how big the powers are, but we are only allowing those primes, right? Only allowing those primes. So I want to find a lot of them. In particular, if I count all the primes that are less than or equal to that bound, like it was, what, 2, 3, 5, and 7, it was 4 primes, right? So in that case, if my bound B was 10, I would want 5 smooth numbers, one more than the number of primes, right? Okay. So what can I do with these smooth numbers? So they don't have to be squares either. They just have to be smooth. What can I do with them? Well, I can write out their prime factorizations, right? Because they're not that big, hopefully. So there they are, prime factorizations, all the primes less than b. Some of those exponents might be 0. And I'm trying to keep track if things are a square or not, right? So what determines if a number is square if you're looking at its prime factorization? Exponents. You look at the exponents, right? If the exponent's even, no matter what it is, then that divisor is going to be, that part contributed by that prime is going to be a square. And if it's odd, it's going to be a non-square, right? So in terms of squareness, I don't care about the number, I only care about the exponents. So let's look at just the exponents. So I can make a matrix of just the exponents, right? And I really don't like big numbers, right? I could have big exponents. My favorite numbers are what? Digital forensic people? What's your favorite numbers? 0 and 1? Yeah, 0s and 1s, right? So if an exponent's even, then when I divide it by 2, it's going to leave remainder 0, and if it's odd, it's going to leave remainder 1. So I can use 0s and 1s to keep track of the evenness and oddness of the exponent, right? Now take a look at that matrix, and note how many rows and columns there are. In particular, there is exactly one more row than there are columns. And what does that mean? Anybody ever reduce matrices to solve systems of equations? You do it in calculus. If you're in my calculus class here, I know you did it. Erica. Calc 2. What's that? You have a free variable, which means that there's some combinations of the rows that will add up to 0, right? And we call that linear dependence, right? The rows are linearly dependent, right? Now, if you add exponents, that's the same as doing what with the original numbers? Multiplying, right? When you multiply two numbers, you add the exponents. Yeah, okay. So that corresponds to multiplying your original numbers. So having all the exponents in the sum of the row being 0 is going to correspond to all the exponents in the product of your original smooth numbers being even. And what did you just find? You found a square. Drop the mic. Not really. But you found a square, right? You found a square. So we can take the idea of detecting smooth numbers and use this linear algebra trick to find squares for Fermat, right? Okay. And I just said that. The product of the corresponding numbers that you began with the rows that you added together, will end up being a perfect square. All right. So here's an outline of the general number field sieve, right? The world's fastest factoring algorithm. So we pick a good polynomial, right? We want that polynomial to give us lots and lots and lots of smooth numbers, right? We're looking for smooth numbers, right? So if we pick a good enough polynomial, it'll give us more smooth numbers, right, than just going through and checking every number for smoothness. Right? So a really good polynomial will do it. We want to look at inputs for that polynomial that not only give us a square, but when you divide it by the number you're trying to factor, you also get smooth, right? So there's two sides of this. You want square and you want smooth, so you can build squares on the other side, all right? And then we can use our linear algebra idea to find a subset whose product is a square like we just talked about. Okay, so here's the big thing, and we'll focus on this for a moment. So on one side, I have what we'll call the regular or the rational side, where we're looking at regular numbers. Those are the outputs. The product of all of them is a square, right? The product of all the outputs is a square. We rigged it to work that way, right? By looking at outputs of polynomials, right? And if I look at the values after I divide by n, look at their remainders after I divide by n, right? They're smooth, right? And I pick only those that I can use my linear algebra trick on so that I get a smooth square in the end, right? Smooth square. So what do I have now? I have all of the outputs. It happens to be a perfect square. They're outputs of polynomials, right? who's a square that's divisible by n, right? And we just found our differences of squares for Fermat. Okay? So that's it. All right. So my summary of all that and why it should matter. So we start by picking a really good polynomial that has a very high probability of doing what? Giving us smooth squares, right? Then we input lots and lots of values of it until we find lots and lots of smooth squares, right? Which should happen better than 50-50, right? If we picked a good polynomial. And then hopefully with our linear algebra trick, that'll produce a factorization. All right? So where's all the research been since the early 90s? It's all focused on one, right? The math research is all focused on one. How do we pick such a good polynomial, right? Anybody that can pick a better polynomial than you can is going to be able to factor faster. Right? So on the computer science side, the research is focused in improving the parallelization of the second step. How do you check all of these outputs? That was Leinster's idea with the optical sensor, right? Once there's an output that's worth checking probabilistically, you save it for later by just looking at the flash of the LED, right? And step 3, how do you parallelize reducing that big matrix that you have in the end, right? Right now, the Bloch-Weidman algorithm is the best. All right, nothing else has really changed until. So this paper, I think, came out in 2013, and my name's on there somewhere. Plenty of time. And the title of it, you'll notice, is this really big number, right? That's my favorite number. So my co-author's there, and he sent me an email shortly after Christmas because he got a Google Home for Christmas. And you can teach Google Home things, right? In particular, you can teach it what your favorite number is.
What's your favorite number?
My favorite number is 49,598 octillion 666 septillion 989 sextillion 151 quintillion 226 quadrillion 98 trillion 104 billion 244 million 512,918.
All right, so there's 32 digits there. It starts with a 4 and ends in an 8. And the paper is about a connection between prime numbers and polynomials. And I like the title because it's obviously not prime. So somehow in there it comes together and works. Okay, so I'm going to talk next for the next 20 minutes or so about this paper of mine and that really big number, why it's so interesting, and how it's related to factoring really big numbers. Okay. So here's the problem that it deals with. There's this famous book from the first published in the early 1900s, Problems and Theorems and Analysis. The subject of that book goes way back. A lot of the problems in there were originally posed by Gauss, right, in the late 1700s, early 1800s. One of them in particular looks like this. So if you take a prime number and you write it in base 10 in terms of its digits, that's all that's going on up there, right? Every number can be thought of as a polynomial in 10 instead of x. Well, what if you replace the 10s with x's? Then you get a real polynomial, right? And this theorem in this book, it's called Cohen's criterion, says that the polynomial you get is always irreducible. If you start with a prime number, you're always going to get an irreducible polynomial, right? So for example, there's this person I know whose name's Jenny, and Jenny's favorite prime number is 8675309. And if you write that as a polynomial, it's irreducible. It doesn't factor. It doesn't split up into other factors. So Jenny has a twin sister who also has a favorite prime. It's 8675311, and that polynomial is also irreducible. And if you don't quite get the reference, there was this hit single by a person named one-hit wonder Tommy Two-Tone by the same title, 8675309. No. Oh, and if you're too young to know what that's a picture of, it's called a vinyl record. A vinyl record. All right. Okay. So a question was posed, and this question goes back at least to Gauss. What is so special about digits? What if you have polynomials that you plug in 10 at and you get back a prime, but the coefficients aren't just digits anymore. They can be arbitrarily large. What happens then? Right? Okay. And that problem was open for a very, very long time until I wrote that paper. And the answer is no. There's nothing special about digits at all. How big can you make the coefficients? Well, you can't make them any bigger than that number that Google Home read to you, right? In other words, there's an example of a polynomial whose largest coefficient ends in a 9, is the same number but ending in a 9, right? When you plug in 10, you get back a really big prime number, yet you can factor that polynomial really easily. And then I proved that anything smaller would be irreducible, okay? All right, so what does this have to do with factoring? Well, since then, some former colleagues of mine, Scott Dunn and Morgan Cole, showed that there's nothing special about 10, right? It works for any other base. So if you take f of 13 and it happens to be a prime, and all the coefficients are less than that big number that they identified, then the polynomial has to also be irreducible, and that's the largest number that you can use. And they found similar numbers for all different bases, actually from 3 all the way up through 20 in their publication. Just last year, it turns out that those big numbers, yeah, they're not that special. As hard as we tried to find all of them, they're not that special. You can generate them for any base with this very nice combinatorial formula. So that's another very nice result. Okay, what was the question again? What does this have to do with factoring whole numbers? So here's the basic idea. If you start with a polynomial that's reducible, with f of 10 being prime, then you would have a factorization, g of 10 times h of 10. But f of 10 was prime, so you have a factorization of a prime, which means what? How does a prime factor 1 times the prime? That means that one of those, say g of 10, has to be 1, right? And so it turns out that if you start with a polynomial, g of 10, that happens to be 1, and try to build a polynomial with all positive coefficients, right, then at least one of those coefficients has to be bigger than the number that's in the title of my paper, right? So there you go. Now you don't have to go read the 20-some odd pages that I wrote. You know. Okay, so I just said that. All right, so what's happened since then? So Carl Pomerantz once asked me a question relating to this, and it was the following. What if instead of f of 10 being a prime, as in my theorem, what if you had f of 10 equaling a product of 2 primes, right? P times Q. So what we're thinking about public key type numbers here, right? Public key type numbers. Well, if f was reducible, would you get a factorization into P and Q, right? If the polynomial was reducible, could you do it, right? So if g of 10 and h of 10 are not 1, right, then that would be a factorization into P times Q, wouldn't it? Right? So the heart of Carl's question was, is there any way in this case that you can exclude or at least characterize what types of numbers will give you back a g of 10 being 1, right? Because then in theory it would work for everything else, right? And my answer at the time to him was I don't know, not at all, not enough information, right? So the flaw in the idea is there's no way to rule out this case of g of 10 being 1, and that's why it doesn't work as a factoring algorithm. Or at least when he asked me the question, that's why it didn't work as a factoring algorithm. All right. So yeah, I gave him an answer, no guarantee, but it sounds interesting enough. Interesting enough that I've thought about it since then, until, I don't know, a week ago. Is that just what was up there, or is that something new? Oh, okay, new theorem. New theorem. So the statement of the theorem is that my big number minus 1 ends in a 7. Oh, I really want to drop the mic on that. So verify that when you subtract 1, you really do get the number below? Yeah? Okay. That's a very profound theorem that gives us a new factoring algorithm. Very profound. Thank you. All right, so how does it work? So the basic idea again, right? How do we rule out this case of g of 10 being 1? Right? Well, it turns out if all the coefficients of f are smaller than that new number, 1 less than my number, then you can guarantee that neither g or h evaluate to 1. You can guarantee it. Right? So as long as the coefficients aren't that big. And likewise, there's a similar number, 1 less, for all of the other bases. Right? So what you want to do in my proposed factoring algorithm is, I think it's here. Is it here? Yeah, that's coming up next. Okay, so what you really want to do is you want to find a polynomial that's reducible and find a polynomial that has an input. Doesn't matter what input it is, as long as it's not 2 for a special reason, right? Because we found the big numbers for every other base in theory, right? So as long as f of some input gives you back p times q, right, and f is reducible, you get a factorization. So f evaluated something is equal to n, or p times q, and the coefficients of f are less than the big number that corresponds to base something, right, whatever your input was, and then you've guaranteed that you factored. Guaranteed that you factored. Okay. So what questions should you have now? Is the first, how can you find such a polynomial, right? You're asking these questions, right? How do you find such a polynomial? And is searching for one of those polynomials faster than the general number field sieve? Is it faster? And if it is faster, then we've just solved a problem that goes all the way back to Fermat, right? A problem that's been a couple hundred years old. All right, and that's all I'm allowed to tell you about that. Another picture. It's what happens when you throw a talk together. You have no idea what's going to happen when you press the button. I'm hoping this won't get me disinvited next year, but oh, okay, we're good. So I'll take questions if anybody has them. That was fun. Thank you. Let's do it again sometime. Yeah. No, not at all, right? Not at all. So if you take n, right, and you write it in base 10, and then replace the 10s with x's, you get a polynomial such that when you plug in 10, you get back p times q, right? So you can generate a polynomial that's related to p and q in that way, and check it to see if it factors, right? Check to see if it factors. If it does factor, right, the fact that digits are smaller than the big number that I gave you would guarantee that that factorization gives you a factorization of n into p and q. Does that make sense? Right? It guarantees that neither of the polynomial factors evaluates to 1 with no information. Does that make sense? Yeah. Anybody else? Yes, Emma. That was you when you were a little baby. Do not call Child Protective Services on me. I don't know where I found that at. Yeah, I don't remember where I found Emma. This is all on the record, too. Maybe we should turn this off before we... Yes. I don't think so, honey. Although, didn't Steve Irwin get in trouble for dangling his kid over the balcony at the zoo? Anybody know who Steve Irwin is? The crocodile hunter guy? Yeah. I'm pretty sure that was in the news when I was in college or something. We got 25 minutes. We can keep doing this. Yeah. So you're talking about Fermat's little theorem, which is different than the Fermat's theorem that I put up, right? So yeah, so for everybody else in the audience, there's a theorem that you learn in elementary number theory as an undergrad if you're a math major, and it's called Fermat's little theorem, and that's actually related to everything. So if you go back, since we have time, let me go all the way back to that slide, right? Nope, back further than that. Hold on. It doesn't want to go back. So if you go all the way back to that slide about how the RSA algorithm actually works, right? Oh, there it is. Okay. That one, right? So the way the algorithm works is that you take your message, which is represented as a number, right? Yeah, use ASCII characters or whatever you want, and you raise it to that power n. I'm sorry, you raise it to an exponent, right, which is called the public encrypting exponent or whatever, right? It's a public exponent. Oh, by the way, I think it's 341 for every standard in RSA. I'm pretty sure it's 341. You have to check me on that. I'm probably wrong. In fact, I'm sure I'm wrong. It's 300 and something, I think, isn't it? Do you remember? No? But anyways, there's nothing important about it, right? You take your message and you raise it to that exponent, and then you calculate the remainder when you divide by n, and that's your secret. That's your secret message, and you send that on, right? So the way it works to decrypt the message and why you need to know P and Q is you need to know how many numbers there are that are less than or equal to n that have no divisors in common, right? That's called Euler's totient function, which you might remember. You call it phi of n from number theory, right? So there's a connection between that value and P and Q, right? So right now, the only way to calculate that value, which you need to decrypt, is to first calculate P and Q, right? And if you could come up with a better way, a different way of calculating that value, Euler's totient function, without knowing the prime factorization, you'll win $1 million as a Clay Institute prize. You'll be given a MacArthur Genius Grant, right? And you will have solved one of the most difficult problems, outstanding open problems in mathematics. Yeah. Instant fame, no more school. Montana. Oh, I don't remember. Okay, so that was the famous thing, right? That you can calculate an inverse for that exponent, right, using Fermat's little theorem, right? And the inverse is guaranteed by Euler's function, right? So Euler's function, the Fermat's little theorem gives you a way using Euler's function to calculate an inverse for that exponent so you can recover back the encrypted message. If I had a chalkboard, I would write it out in one line. It would make so much more sense than me talking about it. Yeah. Yeah.
So earlier, the keys that were
Yeah.
and then showed how many were broken. Underlies all letters of the
So it's very, very problematic, right? Extremely problematic. So if you have the private key for one of these long-term TLS certificates, right, then that's a way in. So let's say Google's TLS certificate, you were able to factor it, right, or found a collision that factored it, right, in this data set, right? Then what could you do, right? You could fraudulently, right, tell everybody that you're Google, and it would pass everybody's certificate check, right? So you get to impersonate Google all over the world, and everybody would trust you that you are Google. Yeah.
For the key space, how much is it for less?
For what?
Having, what I'm looking for.
Let's encrypt. You have to tell me what that is. Sorry, I don't do computers. I just do math. Oh, so they give you certificates, right? Okay, signed certificates. So normally the way those work is you provide the public key, right? They don't generate it for you. You generate it yourself, submit that public key onto their website or to their service, and they give you back a certificate that says this is trusted to have come from this person, right? So that third party has no idea what your private key is. Does that make sense? They're just saying that we are telling the rest of the world that it came from you and you should believe us. It didn't come from him. Yeah.
I know you have the first steps and what we're doing right now.
For a factoring algorithm. Yeah.
What are the other areas?
So not connected with RSA. Or sure. So yeah. I'm probably not the best person to ask that, right? So back when I was a professor, I used to say that whenever you sign up to take a math class, you are willingly subjecting yourself to the bias of that person and how they look at the scientific world, right? So there's two types of cryptographers that I've noticed now that I'm not a professor. There's the type that types in SSH keygen, right? And knows how to use a library and implement it correctly and call themselves a cryptographer, right? And then there's, of course, the side of cryptography that deals with the algorithms itself. How do you prove that something is secure, right? How do you prove that something's secure or more secure than something else? How do you prove something that's vulnerable, right? We call that cryptanalysis, right? And you can say, well, there's two types of vulnerabilities. There's a mathematical vulnerability like this collision algorithm that exists, or somebody coming up with a better factoring algorithm. There's that vulnerability. And then there's a vulnerability that some idiot used MD5 to hash a password, right? And there's some other idiot that used for their password. Yeah, and then those kinds of, but you see the difference in the vulnerabilities. Does that make sense? So what I'm saying is there's two active areas of research, right? One of them a good example would be these people that find and sell zero-day things, right? And then the other side are, the lonely math nerds that sit in a room with no windows and and think math. Yeah. So which one were you asking about? I can't comment on the former one because I don't do computers, but the one that I can't. So what are active areas of research in cryptography? So there is similar collision algorithms, and I took some of these slides out, in digital signatures, right? And they work a little bit differently. They're not a collision of greatest common divisors. So does anybody know how a digital signature algorithm works? You know? Or you have a question? So broken is probably a very bad term. Somebody produced two PDFs that are different that hash to the same value, right? So essentially, in theory, SHA-1 is worthless because somebody found a collision. Well, in theory, right, there's infinitely many collisions out there, right? Because you're taking an infinite space of any file in the world or any message in the world and turning it into, how many characters? 500, well, not that many characters, right? So you're bound to get collisions. Yeah, so somebody just happened to find one or produce one. But anyway, what was I saying about digital signature algorithms and collisions, right? So to make a digital signature, what you have to do is you take a private signing key together with a hash of some document you want to sign, right? And a random number that you generate, that nobody else generates, and then you hand that to somebody and they can verify that you signed it, right? In such a way that you can never deny that you ever signed it to a third party either, right? Because you're the only one that could have signed it because you're the only one with the public key or with the private signing key, right? So it turns out that if you sign two different messages using the same random number, right, you can back compute to the private key, right? And then what can you do with a private key? If you're really mad at Sony, you can use their private key to fraudulently request more data from them, like, I don't know, the payrolls of very famous actors, right? You can do that kind of thing. So that was the big Sony leak that happened over something with North Korea. I don't know. But anyways, so you can go through and you can do a similar test of digital signatures all across the world, right? So there's one area of research that we're focused on. There's factoring algorithms. There's other cryptographic protocols. You might have heard of the discrete logarithm problem, right? It's sort of analogous to factoring in the sense that there's lots of theorems that relate the two, right? So there's a variant of the general number field sieve that will solve that discrete logarithm problem and break that type of crypto. So there's active research in how do you speed up that process as well, right? Yeah.
So, this kind of approach.
So in fact, scanning all of IPv6 is intractable, right? What is it, like 30 million years or something?
Yeah.
It's estimated, it's
Figuring out
horrible.
strategies to find parts of IPv6.
Yeah. I don't know anything about the protocol. I don't do computers.
Because relational user, the IPv4
Yeah.
pattern of zeros or something like that. Nowadays, like most of the mobile so I think the standards would probably have understood.
Oh, I've got another fun one that's probably, it's a topic of research that's at the interface of sort of the vulnerability side of cryptography and the math side, right? So I think it was like last year or so, it was found out that ISIS decided it would be more secure if they rolled their own cryptography standard, right? So they used a variant of RSA, and they thought, well, everybody's using 1024-bit, right? So we would be more secure if we use something that's a bit more obscure than what everybody else is doing. So we should use like 612 bits. I don't remember what it was, but something like that, right? Yeah. And not only that, but because we're the only people in the world using 612 bits, it makes it really easy to see, right? Anybody implementing that algorithm must be. Yeah, so we love it when people try to roll their own cryptography algorithm. Somebody tried to roll their own hash function once too a while ago. That didn't work out so well for them either. Yeah.
So I apologize, I walked late. So were those collisions?
No, multiple people using an overlapping prime factor, right? And yeah, so there it is, right? So if two people both generate public keys, but they both share the prime p, you can calculate it. I mean, you can calculate it with Euclid's algorithm for one of them in microseconds, right? Calculate the greatest common divisor and recover p, and then you just do simple division to get Q and R. Now you have the keys to the kingdom, right? And another reason why these are so dangerous is that organizations love to not pay for separate signed certificates. So every server is using the same TLS certificate, right? So what happens if you have the keys to one of them? Then you're in, and you have the keys to many others. And once you're in those, you have, all these fun little vulnerabilities like MSO8 and things like that you guys talk about in digital forensics, right? And you start getting more stuff from all over the place, right? So one door opens another, and opens another, and you just keep going until you can't go anymore. Yeah, and by the end, you've owned something, right? Is that how you say it? You owned. You did what? Pen testing people when you penetrate somebody's server, you call it owning, or? Okay. Gosh, I'm on the record for that, aren't I, for not knowing that term? Yeah.
Could you talk at all about the signal of what's happening?
What's what?
How the CIA, like the WikiLeaks thing with the CIA?
I don't know anything about that.
So over the past, I heard about it over the past, definitely past week, WikiLeaks released these documents about all the different CIA roads break into common technologies, like smart TVs, and view the end-to-end encryption.
I don't even know what those applications are, sorry. I don't.
It's basically like, rather than just like.
Okay. Yeah, I've sent a text message before. No, I have sent a text message before. I follow you there. So they're like little apps to encrypt your text messages. Okay.
And then you encrypt your phone calls.
Okay. All right, I believe you. I mean, I've called people on my cell phone before too, but that's about it. Yeah, and that was a whole discussion, right? I mean, and the other thing is, everybody loves these buzzwords like Internet of Things, right? How often is somebody upgrading the firmware of their refrigerator? Never, right? Never. So if there was some flaw or vulnerability, right, or some collision, right, that was generated in that certificate that's on there, it's never going to get updated. It's always going to be there, right? And in fact, what we find is that exactly happened. So a couple years ago, in another study about collisions, they weren't using the same algorithm to find them as we are, but what they found was just by collecting metadata on effective servers, right? Just by connecting back to the server and saying what operating system you're using, right? What type of device are you? What firmware version? They collected a lot of information and found that there was about 50,000 IBM enterprise-level servers, right? Whose default TLS certificates came from a set of primes that was 9 long, only 9 primes for 50, used across 50,000 different machines. So what was happening was, so of course they notified the people that did the study. They notified IBM, 6 months before they were going to publish or whatever the agreement is. And what does IBM do? What do they figure out? Well, what they figure out was these things are coming down the production line, right? and a robot is booting them up to do the function check, right? Going down to the next stage, right? The default certificate is generated, going down to the next stage. They're all happening at exactly the same moment in time, right? So the random number generator that's you know, pulling various, like, you know, noise of the sound card and that kind of stuff from every machine is essentially identical as it goes down the line, right? So of course the random number generator or the pseudo-random number generator is going to be generating, or is going to, with high probability, generate the same primes for use. So then again, that's on an implementation side, right? There's some interesting research in mathematics about how do you effectively generate random data. And anybody, if you come across any company that wants to sell you a service to generate truly random numbers, run, right? Alan Turing proved that no machine can generate a truly uniformly distributed data set, right? So true randomness does not exist in the world of computers, right? It's impossible to detect in nature either, true randomness, right? A very interesting result. So the best you can do is a limit point. For those of you taking calculus, you give me some number epsilon, really small number, and you want to approximate uniformly distributed or approximate random that closely. Well, in theory, if you have enough computation power, you can do it. And the smaller epsilon is, the more computation power you have to use, but you can never actually get truly random inside of a computer. Okay. Yeah, like 5 minutes. I don't know. Yeah.
So on the note of like generating random stuff, have you heard of like any?
Yeah, so there's lots of different ways to try to do it. So normally what happens is you take what's called pseudo-random data, right? So you pull the sound card, you pull the mouse position, but that's not anywhere close to uniformly distributed. Well, one of the valuable characteristics of a cryptographic hash function is that its output, right, with, you know, whatever inputs, its output should be approximately or as close as possible to uniformly random, right, or uniformly distributed. Does that make sense? So you take this pseudo-random input, right, that's not really random, because if I knew what soundtrack you were listening to, I could reconstruct it, right? And then you run it through a cryptographic hash function. Now all of a sudden it's more uniformly random, more uniformly distributed, right? So you save that ultra hashed data, right? You save it in a file on Linux. It's called /dev random or dev urandom, right? Urandom I think is for legacy purposes, but I don't know computers. Yeah. So, and then whenever you need a random number for cryptographic purposes, you grab from that file and it's constantly replaced in a stream, right? Well, what if you're doing, you know, millions and millions of calculations per second, right? And you're taking away from that file faster than it's being repopulated, right? Well, you can force, right, very non-uniformly distributed data to come out of it, and that's exactly what a recent attack actually does. I think it's called the drown attack, right? Where you bombard. So first you have to, pwn the machine? You have to get in, right? And then you have some virus or something or malware in the background that constantly makes calls for random data faster than the computer can generate it, right? And then you start looking at the outputs of all the values for cryptographic purposes that have been generated, and well, then there you have it. Yeah. There's hardware-based methods that seem to be better. So there's some very expensive thing that has to do with like measuring how photons bounce back and forth in some tube on a motherboard. Yeah. Yeah, I like that one. That one's a good one. Yeah. So that's the whole point, right? The closer you get to uniformly distributed, which for all intents and purposes is what random means, right? The closer you get to a uniformly distributed data set, right? Uniformly distributed means that every element has equal probability of occurring if you just start picking things, right? So the closer you want to get to uniformly distributed, the more computational power it takes to approximate that. Does that make sense? Yeah. So it's a limit point. If you want, the only way to get truly uniformly distributed data or truly random data is to have a truly random data set, which is impossible to get because you have to approximate uniformly distributed to get it in the first place. Yeah. All right, I'm going to go to the next talk. Thank you, Emma. You only interrupted 5 times. You're a winner. What's that? Most days. Yeah. The building's not on fire yet, so we'll call it a win.
That was the best ever.
We're going to go to Mark's talk now, honey.
I don't even want.
We got one more. It's the last one. And you're going to be extra good and not interrupted,
I
right?
didn't want to go there.
I'm sorry, so sorry.
I wanted to be Catholic, like you said.
That's after. After we're all done, you're going to go see Catherine.
But that's what you
Catherine can't play with you until 6 o'clock anyway. She's busy. Let's go. Come on. Yeah, that's fun, isn't it?
Look. 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 Weird book.